Okay, class, I'm sorry for the delay. We had an ASME meeting in here that did not want to relinquish the space. So, at any rate, I wanted to finish going over some of the homework. I kind of punted on this number 5 last time because I wasn't finished with it, where we were putting our condensate coming back to the boiler house was 240, and it was going into a atmospheric pressure tank, and it was going to be flashing to atmosphere. And we wanted to see if we could come up with some kind of an idea to reduce the operating cost on this. So instead of just relying on the flash steam calculators, which we can certainly do, well, maybe we can, maybe we can't in this particular instance, and I'm going to show you. But I started out just wanting to just show everybody the calculation. I mean, I feel fairly confident that you all already know how to do this, but it doesn't hurt to look at it. And so the 78,500 pounds an hour came from the measure software. Let's see, if I look at a diagram here, wake this thing up, I think this is kind of my base case situation. And I took it, let me make that smaller, not that small. Okay, I took it off of this number right here. And again, we said this before, that measure doesn't have the ability, it's not set up to put this condensate, but this is receiving the 30-pound header condensate, and so the assumption would be that we have 30 pounds here at 240, and it's coming back, and the information given is that it's going into a tank here, which is atmospheric pressure, and so if it's above 212 or so, it's going to generate flash steam. Okay. Now, you can go to the calculators to run this if you want. It's kind of interesting, and so that's what I have here. So I'm saying that my pressure is 30 psig, which is correct. Quality is 0 because it's all saturated, it's all liquid, right? If it was all vapor, it would be 1. That's the definition of quality. And there's my flow rate, and my tank pressure is 0 psig. And here's my flash steam amount, 5,092.73. So that's a little over 5,000 pounds an hour. But let me say, the other thing you can notice here is that the saturation temperature that's assumed in this calculation is 274. So I'm not really saturated. I'm subcooled by, what is that, 34 degrees? So I'm not going to get 5,093 pounds of flash out of this thing. So on this one, because of the way it's given to you, I mean, if it was given to you as saturated liquid at 30 psig, this would be the right answer. Okay, and you can see here's the enthalpy. If it was saturated, that enthalpy would be 243.1. Well, let's go back to my hand calculation here. It's not as pretty, but I think it's more correct. So I use my little calculator, which isn't perfect, but it's pretty good. And so I put in 240 it wants absolute pressure. So 30 plus 14.7 is 44.7. So I put that in, and my enthalpy is 208. That's interesting. That's going to affect the amount of flash I get. So then the calculation is pretty simple. You at whatever your low pressure is, which in this case is 0 gauge, which is 14.7, the saturated vapor is 1150.28, and the saturated liquid is 180.176. And so then here's the little calculation. You just set whatever enthalpy you have in the liquid coming in has to be equal to the enthalpy after you drop pressure. And so the only way that can happen, because when you drop it to atmospheric pressure, it's going to drop instantly to 212 degrees. And so the only way those enthalpies can be the same, this is the enthalpy of the liquid, plus some of this mass has to flash into the vapor state. And so X is the quality, with the amount that turns into vapor, right, the fraction. And that's times just the enthalpy difference from the vapor to the liquid. Okay, so that's just a quality calculation is all you're doing. And so you run that little bit of math and you get 2.923% flashes. Well, so 2.923% of my liquid flow is a little short of 2,300 pounds per hour. So that's what I'm really going to flash. And I looked at that, and I'll be honest with you, when I did this, I just kind of did it to do it. And I looked at that and I said, that number didn't seem to agree with Oak Ridge. And I thought, and I immediately think, Oak Ridge made a mistake. And I'm going to catch those guys at the lab in a mistake. And so I run back to their calculator and I go back to my little steam tables. And so I go, oh yeah, they're assuming it's saturated liquid, right? But it's not, it's subcooled. But anyway, so I go back to my little tables and I go, at 30 PSIG saturated liquid, and it's 243. So my table agrees with theirs pretty much. And so then you just put 243 over here and do the same calculation, and I get 6.483%. And I take that times 78,500 and I get 5,000. This gets about 5,089. And so the tables they're using are probably better than the tables, than that little calculator of mine, but it's basically the same answer. So that explains the difference. So you got to be careful using these online calculators. If you're sure you're saturated and they're assuming saturation, then okay, you'll get a good number and, just save you a little bit of time. But in this case, it gave you a wrong number because of the way that I stated the problem. And I can't take too much credit for that because I just kind of made this thing up on the fly and it just turned out that way. So there's the 34 degrees, which, brings up another idea, another thing, and we don't know how much pipe we have, but so this is like 2,300 and the other's not quite 5,100. So the difference there, if we insulated the bejeebers, that's a good word, out of that pipe, maybe we could get that condensate back at a higher temperature. And then if we can utilize the flash steam productively, we get more flash steam. And, maybe there's something there. Maybe that's something else that we could at least think about to see, what the economics would be on that. Interesting. Okay, well, I'm not done yet. So then what I did is I went back to that thermal compressor stuff, because this is all I can put my hand. I did not go out and do more searching. I probably should have. But at any rate, we had this up there before. Did I email this out? I kind of think maybe I did. Yeah, I'm getting so many emails. You're not even sure. I understand. Lori, I think I did. Yeah, okay. So you have a copy of this, or you can, if you search under thermal compressors, these guys are all, it comes up. It's the first thing that comes up on a Google search. But anyway, so these are all of their definitions. And then, so they've got a little example problem here, which, it couldn't be any better than that. So I just basically took their algorithm here and reworked for our situation. Okay, so I'll show you my numbers. Okay, so I just followed their format. P sub M, that's the motive steam. That's the higher pressure steam that you're going to mix basically with the lower pressure steam in order to get an intermediate pressure. So I figure, if we want to go to the 30-pound header, the next highest pressure we got is 180, and that's significantly higher. So I assumed we would take medium pressure steam, so that's 194.7 psia. And then the P sub S, that's the suction side of the thermal compressor. That's the low pressure, which this is an atmospheric pressure tank, so it's 0 psig, so it's 14.7 psia. And then the discharge pressure, that's what's going to come out the end of the thermal compressor. And in reality, it might be better to run 35 or something, because you're going to have a little more pressure than the header in order to get the steam to flow into the header. But at this point, I just plugged 30 in there. It's easy enough to rework it at 35. But anyway, at 30 psig, it's 44.7. And so that's my suction steam mass flow. That's what's flashing out of that flash tank, is 2,294.5 pounds mass per hour, so pretty close to 2,300. And then you're supposed to calculate the expansion ratio, which is the motive pressure divided by the suction pressure. And this is a pretty good ratio. This is, let's see, now this one's on the chart. So they've got one, I think, for 20 and one for 10. So we're kind of in between those two. Those are the sweeping curves. We'll look at them in a second. So remember 13, and then the compression ratio, 44 is the discharge pressure divided by the suction pressure. So 44.7 divided by 14.7, just a tad over 3. Okay, and then you're supposed to read this entrainment ratio R off of their curves. Okay, so let's take a look. And you can, this is a pretty nice document, man. It kind of leads you through by the nose, so you can work with it. But there is a little bit of an issue. So here's the R we're going to read over here on this scale. The sweeping curves are this, what was it, the E, I forget, what was the name of that? Anyway, that's E. And then the compression ratio is down here. Well, see, the compression ratio was 3. Well, how inconvenient. Ain't that just the way life works? So if you were doing this for a client, what you would do is you would call them up and give them their details, because your case is off of the chart. But you can kind of extrapolate, which is what I did here. And so, this E value, we're 13. And see, I've got 20 here, and I've got 10 here. So, and as this goes out, these get pretty darn close together. So, it's going to be less than 1 for sure, because, say, this is 1, and this is 1.8, so we got to go over here a pretty good ways. So, I think I just held my nose and picked a number. You pick your own number. Your number may well be better than my number, as long as it's, at this level, we're just doing ballpark stuff. So I picked 0.7. First I said, I'm going to pick 0.5. And I go, well, I don't want to underestimate it, So I picked 0.7, but, it's probably someplace, because, this stuff is going asymptotic, or, it's becoming a parallel line pretty fast, and it's got to go out about here on my computer. So, anyway, so if you're going to use this, you got to pick a number. So I picked 0.7. Just to be able to finish it. And I must say, I mean, I would not have I would have some degree of confidence. I mean, I think it's good for swagging numbers. Okay, so then you take the suction steam that you're recovering divided by R, and that's that 0.7, and that gives you the motor steam, the 170 pound steam. How much do we need in order to make this thing work? So that's 32, you know, a little short of 3,300 pounds an hour. So, you know, just in word form, we can recover almost 2,300 pounds an hour of lost flash, and we have to use about a little less than 3,300 pounds an hour of 180 PSIG steam to boost the pressure from 14.7 PSIA to 44.7, which is the header pressure. So then I said, well, okay, so now I got numbers. I can go back into measure, and I can increase. I got to use more 180 steam, but then I'm going to be putting that 30 pound steam into the header, so I get to reduce that. And so I'll let measure evaluate this for me. Now, is it perfect? No, it's not perfect, but it's not bad. It's not bad. If I could find the measure. So I did. And oops, always get my little box in the wrong place up there, I think, sometimes. Let's see what I want to do. Assessment. Let's take a look at this. And we got a lot of, this is a big file. Preheat makeup water, thermal compressor. Okay. So on the medium pressure header, it was 75,000 pounds an hour. So I upped it by almost 3,300 pounds. I took the real number, whatever it was. So, you know, at 3,000 pounds, it goes to 78. So I guess I increased it by 3,278 pounds, or 3.278, because we got to have more medium pressure steam to make this thermal compressor work. But then we get the sum of that, which is over 6,000, and that gets dumped into the low pressure header. And so it goes from 40 down to about 34,500 pounds an hour. Okay? And then I just say, well, okay. Tell me the result here. And we got so much stuff, we got to scoot over to find it. There, thermal compressor. So let's see, this one I got 95, this is fuel. This is, so that would save, according to this, almost 96,000 in natural gas. Well, that's not bad. And then I get another 3,000 in water. So I've got savings pushing $100,000 a year. And that's probably a $100,000 project, give or take, you know, 75, 100, 110, something like that. So this is ballpark a 1 year payback. Well, that's not bad, you know. Go put some money in your savings account at the bank and see what they're willing to pay you for it. After a year, maybe you can go to McDonald's and, you know, get a quarter pounder cheese and a Coke, you know. I mean, the interest you're getting is just nothing, you know. So, and this is probably more sure than investing in the stock market. So, you know, if a company has $100,000 to invest, this is probably a reasonably good idea. Okay, that's one idea. Now, this other one, man, I had my life's been hectic today. So I have not even run this one to ground yet, but I'm going to show you. let's see, is this internet? Oh, come on now, don't. There we go. Okay, so flash, steam, vent, condenser. Okay. Aha. So they make these devices. Let's just look at a picture. I think that's, let's see if that's a pretty good picture. Yeah, there you go. So here's my atmospheric pressure tank. And so this vent condenser is just a heat exchanger. And you got to put a cold fluid in, and this is like a shell and tube heat exchanger. And so that flash steam flows into this thing, and it makes that steam spread out across the outside of all those tubes. And if you got something cold, like it could be makeup water, it could be, if it's Campbell's Soup Company, it could be water that's going to make soup, that you're going to have to heat up. So every bit of energy you can put into it before it gets to whatever it is going to heat it up is going to use less energy. So here you go, and you've got a fair amount of energy that you're just throwing to the atmosphere. And if we condense it, guess what? If we condense it in that thing, in liquid, it'll fall back in the tank, and we also save the water. So that's pretty cool, So this is what we're looking at. Now, again, like I said, I've not run the numbers on this, but so that's an atmospheric pressure tank. So that steam that comes out of there is saturated steam at atmospheric pressure or at 212. Okay, so we've got the enthalpy. So we take the enthalpy of that steam, and we're just going to condense it to liquid in that heat exchanger. So we take the enthalpy of the liquid, it's just HFG, is what we're going to save per pound. It's what, not quite 2,300 pounds. So we can get some kind of an idea how much we can save just by doing, using our calculator, which I do have. Okay, so let's do that real quick. This is what I was going to do and get on my paper, but this one never made it to the paper yet. Oh, man. All right, so here's my little. Well, and come to think about it, we had those numbers, right? It's, what was it? It was 1150 on the saturated vapor and 180 on the saturated liquid. So it's 1150 minus 180. So it's 970 BTUs per pound that we condense. Okay, and I'll just run 2,300 pounds times 2,300. Oh wow, that's 2.23 million BTUs an hour. So I divide by 1,000,000 to get it in millions. Yeah, 2.231 million BTUs an hour. And if we put that heat directly in a fluid that we were going to heat with some sort of a heating device, say using natural gas, that heater would probably have an efficiency of 80%, is kind of a standard number. So I can divide this by 0.8 because I don't have to get this gas out of this water heater or liquid heater, whatever it is. So divided by 0.8. So now that's 2.789 million BTUs an hour. And what was our gas price in here? $3.50? I think it was $3.50 a million times 3.5. Well, that's $9.76 an hour times, if it's a whole year, 8760. Well, that's 85,500. So that's another option. And we get water. We'd have to So it's probably another, I don't know, $3,000, $4,000 water. So it's probably in the ballpark of 90,000 doing this. So I've got 90, 100,000 in savings. The question is, what is the cheapest, most feasible, easiest way to attack this? And that's where you got to sit down with the guys in the plant and say, okay, boys, here's what we got. You can show them a picture of the vent condenser. You can show them a picture of the thermocompressor. I think the vent condenser is probably a little simpler. It's just a heat exchanger. But, you know, do you have an appropriate flow that you can put through there? You know, maybe you could just, if you don't do the blowdown heat exchanger, maybe you, because that blowdown heat exchanger is going to heat up the makeup water as well. So then it's a question, you know, you've got multiple energy sources. You can't dump them all into the same stream. If you don't have another stream, then you pick the one that has the best bang for the buck and don't do the other one. So anyway, so that's pretty good. Okay. Now also, I wanted to show you what I've done on this combustion air fan deal. Okay, so well, maybe we should read it. Let's see, that's open. Pretty sure it's open in Word. No, that's the email list. Let's try this one. I believe that one's a little better. Well, let's see. So here's where, someplace down here. There's the information. Boiler combustion air fan has an induction motor rated at 125 horsepower. Combustion airflow is regulated with discharge dampers, which we now know are extremely inefficient. Measurements taken during the assessment visit on the operating fan are VAB. So, you know, you've got phase A, phase B, phase 3. You've got 3 different wires in front of you. You open up the panel. You hope nothing bad happens, like no electricity jumps out and grabs you, called arc flash. But you reach in there, you got your voltage probes, or just touch probes, or little clips, and you clip on A and B, and the meter reads 475.2. So that's the A phase to B phase voltage. And then you go, okay, and then I go AC. So I leave the clip on A, and I go over to C. You know, probe or a clip or something. I get those touching. Oh, 471.9. And then I leave the one on C and I come back to the middle one, and that's B. So I get voltage BC, 477.6. So then what I do is I average all of those to get my average voltage. And then on the current, I have to go around the wire. So I have a little clip that I clip around one of the wires. You know, it could be, you know, over insulation, all that. You just got to get that clip over the wire. And really what you do, you clip on all 3 of them and you read all 3 phases at once. But anyway, so you read, and so just that one clip gets you the current. It's measuring the electromotive force around the wire and transducing that into a current flow. And that current reading is irrespective of voltage. So it measures the voltage independent and then measures the current. And then the meter, if it's a good meter, does a calculation and calculates the power and calculates a power factor, and it measures the reactive and all that wonderful stuff. Okay. So on phase A, we get 125.4 amps. Oops. Oops. That should be phase B and phase C. There seems to be a little hitch in my get along when I was copying and pasting. So I'll do here. Maybe we should fix that right now. So if I use this again, I won't be so embarrassed. You know, nothing like doing your editing in front of your class. But anyway, so we'll get that saved away. All right. So, like I said, current on A is 125.4, the current on B is 128.1, and the current on C is 121.9. Add them together, divide by 3. That's what we use in the calculation. Now, let's go down and see what you were asked on. I think this is number 6. Okay, you want to investigate a variable speed drive or a variable frequency drive. I've used both for the combustion air fan. Assume the needed fan capacity is roughly the percent load on the boiler, which is, I think, well, okay, so that's a good point. Well, we'll check that, percent load on the boiler. Because we know capacity is 250,000 pounds an hour. That was given to you in the initial information. VFD losses are, I left that off of mine. I'm going to have to edit my solution. You know, I just can't make a good grade on my own homework. You know that? That's one reason I like to go over it in class. I find all my mistakes, because the worst thing is to grade everybody from an incorrect answer. And you go, oh crap, that's no good. So anyway, we're going to assume VFD losses are 3% of full load motor power. The drive cost $150 a horsepower to purchase and install. I mean that to be total. So for the cost, I took 125 horsepower times 150, so that's 18,750 is what I intended, but you might have interpreted that. That's not very well written. Anyway, calculate the project savings, costs, payback, and IRR. Okay, so it'd be good if I read my own problems. But anyway, so I just went ahead and did this in Excel. I did in Excel, I can show you, and then we can all chuckle about what I did wrong. But anyway, so there's my amps, if I punched them right, and then that's just the average, okay, 125.133. There's my volts, so I got my average 174.9. Okay, now you got to figure, you got to come up with a power factor. And I don't know what y'all did on power factor. I have some software. I kind of, you know, I leave some of this kind of open-ended just to see, you know, give people enough rope, maybe just like me, I'll hang myself. But anyway, this is out of some pumping software, but these are motor characteristics. And so if you put in the motor size and the hertz, and you know, a voltage, I guess I could have changed the voltage to what we had, but that's just kind of a standard voltage. And then it will show you the efficiency. Let's see, this is efficiency, I think. This is power factor, and this is percent full load amps. Okay, and it also will project that the full load amps, and it has different efficiency classes. So if you say energy efficient, your full load amps is a little lower than you say standard efficiency or whatever. So, you know, there's some variation there. And the only way you would know would be to go look at the motor. And, you know, it maybe even, if you really wanted to know, you'd have to contact the motor manufacturer or look online for that particular motor and see what its efficiency is, whether I had picked the right efficiency class. But anyway, I just ran energy efficient. And so I'm looking at this 135.9 as full load amps. And so what I've done here, I think this makes sense. Y'all decide. So then I said, well, what my average current is 125. That's in G27. So if I divide that by 135.9 times 100, that's telling me that my percent full load amps is about 92. Okay, so this thing pretty well loaded. You know, you can come back over to here, down where I see the scale. So see, there's 90. There's my percent full load amps. And so at that same 90, 92, I'm over here a little bit. So you can see that's my efficiency. I mean, it's right on peak efficiency. The efficiency looks like it peaks a little bit here and maybe slides off a little, but it's pretty close. And then there's my power factor. So it's not quite full, but it hasn't dropped much. So then this particular chart, and Oak Ridge Measure has a similar device. Measure may be better than this one, I don't know. But if you look in the Measure tool, you've got this same kind of information built into it. So you had a calculator, that one easily accessible to you. Anyway, this is older software, and old guys always want to use the old stuff that they use more than the new stuff. So anyway, so if you look over here at efficiency, at 100% full load amps or 100% load, it's 95.24. At 75%, it's 95.33. I just said, shoot, for me, it's 95. That's plenty good enough, because I know that's a good number for efficiency. Well, and then you look at power factor. Well, we're 86.67 at 100%. We're down to, what, 84.6 at 75%. I'm down a little bit. I think I just used 85. You could use 85 and a half. You could do an interpolation in there, whatever. Or you could use the Measure tool stuff, and it'll probably give you an exact, just one number. But anyway, okay. So then for kW, well, what do I got? Volts, guess what? Volts times amps times the square root of 3 times that power factor, G30, 85%. And you got to divide it by 100 to get it into a decimal point, and then divide by 1,000, and that'll get you kW. So I'm at 87 kW. And then full load kW, well, it's a 125 horsepower motor, so times 0.746 converts, and now that 125 is shaft output. But I'm comparing this to measured power, right? So I have to divide that by the motor efficiency. Makes it a little bit bigger. So I take the 125 times 0.746, and that's 125 expressed as kW, and then I divide by the 0.95, and that makes it input power instead of output power for the motor. And that extra percent is lost as motor heat and friction in the motor. Okay. So, I mean, I'm wanting to see what my load is on the motor and all this stuff. So that would say my full load input kW is 98.16. Well, then I'm just calculating my percent load. Kind of see, well, I was like 89, 90%, something like that on the motor. Okay. Let's see. Now let's go on down. So at 90%, now there's a couple ways you could do this. I think I sent you out these curves. This thing's getting kind of messy. All right, so then I pulled numbers off of these curves. Now let me see if I can remember what my rationale was for the numbers that I pulled. Okay, so I went to the Measure tool, and I looked at the boiler load, and I just went to kind of the basic after we tuned it to 5%. Okay, so if you go back to Measure, let's look at diagram, not this one. Let's make sure I get the right one. Okay, so 149, there's my steam load, 149,490. So what's that about? I think I just said 150. 150 divided by 250 is 60%, but now that looks like 60, but now I think what I did is, okay, Let's go back to this. I should take notes on this stuff. I get myself all fired up and I forget what I did. 60% load. Well, I think to be conservative, and I mean, I'm not going to grade anybody down for doing this or not doing this, but there's always a question between, say, a damper position and a flow rate, and because I mean we're estimating all this stuff. So at any rate, I talked myself into using 70% as the boiler load. Not quite sure. Might redo this at 60, but I know I had some rationale for it. I just don't remember what it is. But at any rate, so if you come down here at 70%, which is what I believe I did, see here's 70%. It's saying that if the boiler load is 70%, that the fan would be 70%, okay? And so at 70%, you say that's going to cross right about there. That's right on 90% full load power, okay? That's with dampers. If you did this with VFD, I don't know, what is it? There's 40, I don't know, 37, 38%, something like that, however you want to read that. And then I pulled those numbers. Okay, so G36, damper. Let's see, what is this? This is G36. Percent load. Yeah, okay. So, well, what is it? G34. That's the percent load on the fan. Okay. And so that's with damper control. Okay. And so we're at 89% of fan power. Then the estimate on the VFD, that comes from the curve, would be about 36% of full load kW. And so 36% of the full load kW, which is the 98 number, is right here. And so that's 35. And then you subtract the two, and you're going to save about 52 kW, and then 8760 hours per year. So there's kilowatt hours saved. There's cost per kilowatt hour, annual savings. That's the estimated cost, and that's the payback. What I didn't put in here, let's see, so what I need to do, VFD kW, this needs to be times 1.3, because there's 3% VFD losses. .03. There we go. So it makes a little difference. So you have accounted for the VFD losses. So that's one way. The other way, which I think I encourage you all to do, is to use the ABB calculator. And I haven't done that yet, but I'll probably do that and bring it in next time and see if I can stumble through that one like I stumbled through this one. But anyway, you get the idea. There's different ways. There's no perfect way to do this, you know, but you're looking for something that you can at least trace back to measured data or a theoretical calculation that is agreed upon by the industry or something. You know, you can't just make up numbers out of the thin air. You've got to base it on something that, you know, you can make an argument that has some validity. Okay. Wow, I thought I would remember that better, but anyway. Okay, so let's, we're getting close to wrapping up steam. We'll probably make an announcement on our steam test. I would say we'll have our steam test before fall break. So we're just about done in steam. It's time to move on. So, you know, and, you know, there's more slides here than we can cover. There's almost 400 slides here. I can't do all of that and the other stuff we need to do. So you'll be tested over the stuff that we discuss. You know, other sections, I might tell you to read certain particular things that I might ask you a few questions on, but basically the test will be over what we have covered. Okay, so this is back in this section looking at impact, cost, and steam leaks, steam leak tables, all this sort of thing. So I wanted to start here. So Measure will calculate this for you. The software tool, it really takes a software tool to do this, but this is looking at the value of steam at different pressures, okay? And the big variation is whether or not we have turbines present. If we're doing cogen, say that high pressure steam is worth a lot, it's worth more relative to low pressure steam if you're going to put it through a turbine and make electricity, because that electricity saves you money. You know, if you're just using it in the process, then there's not that much variation between high pressure, medium pressure, and low pressure steam. And so that's what that middle column is. This came out of SSAT, I'm sure. But so for this sample boiler, we see that high pressure steam is worth $7.70 a 1,000 pounds. Medium pressure is $7.49. Low pressure, $7.47. So there's a little bit of difference, you know, because you've got more energy and you can do a little more with it. But in general, there's not that much. But look at what happens when we start putting power gen. You see, we see a bigger drop between the two, especially between the medium pressure and low pressure. And so what these programs do to calculate this is they have a base model and they will increase the amount of, say, high pressure steam by 1,000 pounds. It does it automatically as part of the calculation. And then it calculates the overall cost. And so it knows to provide that 1,000 more pounds of high pressure steam costs me this much money. Okay, or you could reduce it, but you know, you can increase it or reduce it. And so it goes through on each one of those, and it increases the high pressure, calculates the cost, then resets it to what it was before, then increases the medium pressure, goes through the algorithm, and likewise. And so these are not very easy to do by hand. People don't do these things by hand, but the computer software can do it easily. Okay, cost of steam leaks, I don't know. This is dollars per year. These tables could be cast. You know, you just give it a value of steam. In this case, it's $10 per 1,000 pounds, and we are using the 0.6 discharge coefficient. And then, so instead of a leak rate, it just runs through the annual, assuming 8760 hours per year. And all that sort of thing. Yeah, I mean, you can program this for yourself and then put in whatever number of hours per year that you want. But in general, when you just see a leak table, it'll be 8760 unless it says otherwise. This is just a slide on this sharp-edged orifice. You know, so there's a picture of an orifice that somebody, you know, Jeff or somebody in the shop made and put it into a test rig and, you know, took the data. So in general, sharp-edged orifice will pass about 60% of the steam loss compared to a dull-edged orifice. Now, how sharp is sharp? How dull is dull? I mean, I don't know. You can go into literature, I'm sure, and find specifications on some of this stuff. But anyway. Okay, pipe failures. You know, I mean, and this is, I think we've said this before, but it's an order of magnitude estimate. to give the plant or maintenance, whatever, you know, some kind of an idea how much is, if you let this go 6 months or a year, how much are we going to lose by doing it? And oftentimes there is a safety issue because steams can cause safety, you know, can damage people, harm people. So as an example, the leaking valve shown, it's been estimated that it's passing the steam equivalent to a 1/4 inch diameter sharp-edged orifice. You know, and everybody here might have a different estimate. So let's do an order of magnitude estimate. So steam pressure was 265, which is about, if you figure 15 for atmospheric, it's 280 psia. Steam was valued at $4.62 a thousand. So if you use Napier's equation, and I think we got the numbers here on the next page, predicts the steam loss to be 424 pounds per hour. Loss tables, actually, I ran through the loss tables, had to interpolate, and I got the same number, which made me think that I didn't make up the loss table, so that somebody used Napier's equation to make up the loss table is what it looked like to me. But for a year, if you multiply that out, we lose 3,714.2 K-pounds. So that's valued at a little over $17,000. You know, it's probably a good idea to fix the leak. Now, you know, it could be 15, it could be 20, but, you know, it could be 10. But still, you know, you've got some kind of an estimate. And of course, I think you guys know how to use Napier's equation by now, but that's the basic equation, 5143 times the area of the orifice times the pressure of the steam. Area is in square inches and steam pressure is in psia. And so for the 1/4 inch orifice, there's the number 0.049 inches squared. Plugging in and putting in the 0.6 for the sharp-edged orifice, it comes out 424. In the tables, you have to do an interpolation because we're 265 here. But if you do, there's the interpolation. It comes out 424. How about that?
I got a question. For the mass flow rate of an area multiplied by pressure, where does the rate factor into? Is that 151.43?
Is what now?
The rate, like it's LBM per hour, but it's area multiplied by power.
Oh, well, see there, it's all built into the 5143. Okay. There's units in that. Okay. No, I mean, this is, yeah, no, you're going to have to put whatever units you want on 5143 to make this work. See, that's an experimentally determined coefficient is where that comes from. That's not theoretically derived. Somebody took measurements and just set it up like that. That's a very good question, though. Okay. So that just shows the calculation that we went through. So that's pretty straightforward. Okay, so this comes from an actual trap survey at ArcelorMittal Steel Company. ArcelorMittal is one of the biggest steel companies. They're actually German in the world. And they have a huge plant outside Chicago at Burns Harbor. You got to punch up Burns Harbor ArcelorMittal plant. And I mean, I was up there for a week, and I mean, that place is huge. But they had, Trapco is a company that does steam trap surveys. And so they provided me this information. I think I put some of this stuff in my report, whatever. But they surveyed the traps. So steam, you see chemical area, steam traps, steam leaks, chemical area 75. So anyway, this was their estimate on the dollars per year. I think we were at 277,000, something like that. So they, you know, companies actually do pay, if they can't do it themselves, they'll pay another company to come in and survey all their steam traps, somebody that really knows what they're doing. Okay, let's look at distribution system losses. And there's some infrared images that are very common. That middle image and the right image are from a little company in Cookeville that does chrome plating. Years ago, they had, I mean, it's not a very big, what is it, Cookeville Plating, something like that? We did a lot of energy assessment. I know the guys, I play golf with them sometimes. But back in the like 60s and 70s, when all of like door handles and things and fittings on cars were chrome plated, they did like half of General Motors' work here in Cookeville. I mean, these guys made a mint. I mean, they're still in business, and of course, all that's moved on to, you know, everything's plastic and foil coating. It's all different now. But I mean, they're still doing work out there. But I mean, they had a major money-making operation going. They were very, very fortunate. Anyway, so they had this small little boiler, and they were making some steam. Went in there and looked at it with the infrared camera. They did not have one stitch of insulation on their whole steam system. Not one. I mean, I've seen a lot of insulation falling off stuff where they used to have it, or they cut it off to do maintenance, or they did something. But these guys didn't have a stitch. And so, you know, and that middle, that shows the kind of reddish pipe is cooler. That's the condensate pipe. And the white yellowish pipe is the steam pipe. And, you know, they're not very big. What are they, inch and a quarter, inch and a half, something like that. But, you know, I mean, it was a decent sized place. I don't know, 3,000-4,000 square feet, or maybe 10,000, I don't know. And they had these pipes running all over the place. And I mean, I sat down those guys and I just started laughing. I said, man, you guys, never seen anything like you guys. You have a steam system without one stitch of insulation. You're the only people in the whole world that do that. And they started laughing. They said, well, will it save us some money? So that next night, you know, we measured all the pipe and all that stuff. And I'll show you some little software. And it came up something like, I don't know, $5,000 a year. And so I went back out there because I knew him. And I sat down, I said, you know, it's someplace around $5,000-6,000 a year and all that. And I said, oh, man, that's a vacation. That's an extra vacation. You know, we can take the family and go, you know, we'll go to Pigeon Forge or Gatlinburg or, you know, Destin. I mean, that's a nice vacation. Yeah, we'll do that. So I had to go back out there about 2 weeks later, and they had insulated their steam system. And I have some pictures that I can't find. But what they did, they went to Lowe's, and, you know, you can buy this just straight insulation that's split, and you just clip on the pipe, which is fine. And they did that. They didn't insulate the elbows. Or you can get insulation with the elbows, but they said, we're not going to worry about that. So all of the straight pieces had this on it. And then, you know, so if you shot it with the camera, it was all dark, and all of a sudden the elbow was there, and the fitting here, and the T, and all this stuff. And to be honest with you, it looked like hell, but it was insulated, you know, pretty well. And then this tank, this was what functioned as their deaerator tank. It's not really a deaerator tank. They're just dumping their condensate back in there. And you can see it wasn't insulated, not a stitch anywhere. And so you can see the water level in the tank with the infrared camera. You see that white part on the bottom is the hot water, and then above that, it's just hot air. And you see the little vent on it. It's cold, so it's not flashing. You see, if it was hot enough, you'd have flash steam, and that little vent would be hot, but it wasn't. So what they did, they bought some bat insulation like you would put in your attic, and they got that stuff, and they wrapped it around that thing, and they got duct tape, and they taped it, and then they cut some pieces for the end, and they stuck it on there, and they duct taped it this way, and they duct taped it this way. And if that wasn't the, by God, awfulest looking mess I've ever seen in my life, but what could I say? It was insulated. And I don't know, they probably didn't get the full value for their vacation. Maybe they had to go to, like, Sparta or something, I don't know. But they did save some money. So anyway, then on the left is very common. That's up at the top of a boiler where the steam is coming out. There's always fittings and valves and all that stuff up there. And that stuff is rarely insulated. You can get valve insulation, little jackets and covers that you can put on there, like, that has little lace-up things. It's kind of like lacing up the kids when they go out to play, in the snow or something. But you can insulate all of that stuff. And if you think about it, there's a number of square feet up there. I mean, a big valve, a big pipe or something like that, this big around. I mean, just a short stretch of it may have 3, 4, 5 square feet of surface area. And over the course of a year, I mean, that sees your full steam temperature. So it's pretty hot. So there's a pretty good payback in insulating that stuff. So anyway, that's one of my favorite slides. I love it. Okay, so here's a little scenario. Assume we have 30 feet of uninsulated 12-inch diameter high pressure steam line at 900 degrees. Whew, don't want to bump up against that. We'll use the 3E Plus insulation program to evaluate the savings from installing 4 inches of calcium silicate insulation plus an aluminum jacket. The impact fuel is natural gas, valued at $485 a million, and the boiler efficiency is 78%. This is 3E Plus, and I have it live here, but we'll go through the slides here for a minute, and then I'll fire it up for you. This is a super little program. It's free. It's downloadable. I would encourage you to just Google, download 3E Plus. You can get it through USDOE. It's put out by the National or North American Insulation Manufacturers Association. There's a guy retired over here from chemical engineering, Dave Yarborough, is an insulation expert, and he went one day a week to Oak Ridge for years, and Dave was one of the people that built this thing, and Dave is first class. So this is a really nice piece of software. It's so easy to use, and I just can't say enough good things about it. And this is what some of the inputs look like. You have a descriptor, and you have different, it could be horizontal pipe, vertical pipe, it could be a flat tank, it could be a vertical surface. Got some different orientations, geometries built into it. Different standard units, I don't know, I don't ever change that. I've never messed with it, I'm not real sure. And you can, it will give you slightly different outputs depending on what you request, the calculation type. This one's set up for heat loss per hour. You can get heat loss per year, and you can get a bunch of different things. It just changes the output a little bit. The process temperature, so this would be the temperature inside the pipe, the steam temperature, 900, ambient, 75, and then the pipe size. And it also, you can put in a wind speed, and it will go from a natural convective situation to a forced convective situation, which will drive up the heat losses significantly. So you do that, and then if you click on these little pull downs, it's got, I don't know, it's got PVC, copper, steel, stainless, and if you want to, you can go into the background and you can add materials. You can add your own materials if you want to, but you've got to have all the physical, parameters, the density, and all the stuff that it wants. And then you can click on this guy, and I bet it's got 30 different types of insulation. That's the hardest part, is knowing what daggum type of insulation to select, because some of them are trade names and all this stuff. But I mean, if there's a common insulation, it's in there. And so in this case, calcium silicate is a very common insulation for high temperature steam pipes. So that's why this is called up. And then the calcium silicate would always have to have a jacket. You can put aluminum, you can put canvas, you can put aluminum bright, shiny, new, you can put aluminum dull, tarnished, you know, it's got lots of options. I'll show you live here in just a little bit. So, and then here, if you click on this, you can specify one thickness, or you can let it vary the thicknesses, and it'll give you like, I don't know, a 1/2 inch, 3/4 of an inch, inch and a half, 2 inches, 3 inches, 4 inches. I'll give you a big table and give you all the heat loss characteristics for all those different thicknesses of insulation, so then you can pick which one you want. If you already know, you can click that vary, and you can select like 3 inches or 4 inches or 2 inches, and it just gives you that line. So it just, again, it just changes the output a little bit. So see, this one says vary, and so that's the kind of data that you get. You get the bare pipe insulation or situation, and there's your surface temperature. It's 900 inside, and there's a little drop across the wall thickness. It's projecting 892.7. And here's the loss. This is BTUs per hour per foot of pipe. And so that's 18,610 BTUs per hour per foot. So if you've got 100 feet, you multiply that by 100, and that's your loss per hour. Pretty easy. If we put, let's say we put 3 inches on it. So then that surface temperature, and see, the surface temperature is of interest because for burn protection, you want to get it, I think, below like 140. 140 is kind of the temperature at which you just can't hardly hold on to the pipe. 130, 120, you can hold on to it. It may be warm, but you'll be okay. At 140 and above, you're just not going to do it, you know. And so you can see, if I'm wanting to get this down, if I want to get this below 140, I'm going to have to put 6.5, 7 inches of insulation on it, because 900 is pretty darn high. Okay, and then this is the heat loss. You can see how it goes down. And so your savings would be if it wasn't insulated, your bare pipe loss, say if you put 3 inches, you go from 18,610, 3 inches, it would go to, what is that, 594.4. So you subtract those two, and that's what you're going to save by adding the insulation. And then the efficiency is the percent reduction. So, you know, that first 1/2 inch, you go from, 18,610 to 1,877. That's an 89.92% reduction in heat loss. That's what that number is telling you. Okay. Same thing. Oh, okay. So this is you can also, yeah, okay. So this first two, this input screen is if you're over here on this tab. If you put in cost of energy, you get slightly different inputs. Here you've got the same stuff, but it wants to know the fuel type, natural gas, the energy content, BTUs per cubic foot, and the cost and the efficiency. So you can input that as well. And so this will give you dollars instead of just energy, because then it can translate from the energy loss to dollars. Yeah, and there. So there you go. Now this one, how are we doing here? Okay. So, you know, similar type stuff, but this is dollars per foot per year. And then this is heat loss, BTUs per foot per year. And this is savings, dollars per foot per year, at different thicknesses of insulation. So if you went 3 inches of insulation on this guy, you would come down here, and it would save $806.70 per foot per year. So, you know, if you had 10 feet, it would be 10 times that. If you had 100 feet, it'd be 100 times that. Okay, so bare pipe heat loss is 18,610 with 4 inches of calcium silicate insulation plus aluminum jacket. The heat loss drops to 485.3 BTUs per hour per foot, saving 18,124.7. Natural gas savings are $811.60 per foot per year per foot, or 24,348 for the 30-foot section. Assuming a cost of $80 per foot, it would be 2,400. Simple payback is 1.2 months. Hopefully there's not a lot of 900-degree steam pipe that's not insulated. You would hope. But anyway, so this is a pretty aggressive example. Most of the time I find something at most 2, 3, maybe 4, 350 degrees or cooler. Like condensate pipes will be, 180, 200, 210, something like that. Tank insulation. So assume we have an uninsulated rectangular tank, 24 feet long, 12 feet wide, 10 foot tall, containing 20,000 gallons of an oil water mixture at 170. So we can use 3E Plus program to evaluate the savings of installing 2 inches mineral fiber insulation plus a jacket. And there's the fuel, 485 and 78%. So here it's all pretty much the same. We just have a different geometry. So flat surface vertical, so this would be for the sides. Process temperature 170, ambient 75, wind speed, etc. And here, I don't think I mentioned this before. Here's the jacket material. You've got a pull down here that's got all of the different jacket materials. So let's see. You run this one, and so this is the energy output, and so you see, what do we say, 2 inches? So that surface will be about 84.5. We're going to go from 183.9 down to 13.2 BTUs per hour per square foot, and so that's a 92%, almost 93% reduction in the heat loss. You can run the cost calculation. And so for the 2 inches, we're going to say per square foot, we're going to save $7.64.1. So that's just taking those numbers, multiplying it times the area on the sides, 2 inches mineral yield. So we're $5,500 for 720 square foot on the sides, and then you can run the top, duct flat top, the energy here, and then you can run the cost, bingo, and so we're going to save $8.80 on this one. 2 or 881. So the same sort of thing. So it's 240 square feet on the top. So that's another 76. So at $20 a square foot, the cost is, I guess the total for the top is 2,113, total 7615. So that gets about a 2.5 year payback. Okay, so let me pull up this 3E Plus. Here it is in living color. So here's the energy tab, basically what you're saying. Descriptor, that's just for you, keep up with what you're running. There's all of the different configurations, pipe horizontal, vertical, tube. Don't ask me the difference between a pipe and a tube, I don't know. Please don't ask me that. You know, anyway, you got shells and stuff, but so there's your units. Like I said, I've never really messed with those. Different types of reports. You can run personnel protection, condensation, control. So it changes the output a little bit. I'm typically looking at heat loss per year, heat loss per hour, something like that. Process temp, ambient, wind speed, and so if it's pipe, it wants to know the pipe diameter. It's got a whole bunch of them in there. There's we got steel, stainless, copper, PVC built in. There's the say if I want to fix it, then I just type in the thickness of insulation that I want it to analyze. And there's some of the insulations. So you can see, I mean, sometimes you have a hard time figuring out which one you ought to be running. But, so all the way down to there and all the way up to there. So you got a pretty good choice. What is that? About 30, something like that. And then here's your jackets. You got all kinds of things. Aluminum new bright, aluminum oxidized in service, stainless steel, bright and dull, iron steel, copper, painted metal, galvanized steel, aluminum painted canvas, roofing, felt, and black mastics. All kinds of stuff. So pick what you want. How about alignment of bright, shiny, new? And then you just put calculate and bingo. You got your numbers. You can do environmental stuff. It will, if you calculate this, you get CO2. What's that? Pounds per foot per year. CO2 in metric tons per foot per year, and NOx based on the fuel type that you put in. And then you can run the economics tab. And that gets you your cost numbers. Dollars per foot per year, 1,000 BTUs per foot per year, and savings dollars per foot per year. And then I don't know, I don't mess around with the options too much, but you got general options, you know, insulation materials, fuel types, base metals. And you can add to these if you have something that you need to run that's not in there. So anyway, that's 3E+, really nice little program. Encourage you to download it. Okay, so there's more of this. I think I may skip through this. Oh, that picture is of interest. That shows one of those jackets that you can purchase, and you can wrap up those valves. And really, I mean, a big plant may have hundreds and hundreds of uninsulated valves, and the overall valve loss is significant because a lot of times they see really high temperature steam and have very high surface temperatures. Now, when I would estimate that, I would probably do that, and again, there's no perfect way. One way I've done it sometimes is to just assume it's a vertical surface, and then, yes, sir. Oh, have I run long? Oh, yeah. Well, you know, no extra charge. Don't worry about it. I guess I was on a roll, huh? All right, guys. We're going to finish up steam next time. Be looking for an email with a link, and I'll be sending you a bunch of pumping files. So we're going into pumping systems next. So have you a great rest of the day. Someone finally had the courage to stop